Hello. The purpose of today's video is to talk about a specific subset of counting principles dealing with permutations and combinations, but specifically where there are exclusions. So exclusions would be, just like this first example, we need permutations of the letters in the word kitchen, but we have to exclude all of the permutations that begin with the letters KI. And then a variation on the question, K and I are not in the first two letters. So it seems like the same question at first, but the first one says K and I cannot be the first and second letter respectively. And in this one says we cannot have K, I, or I, K to start our permutations. So there's subtle differences between the two questions. But once again, this video is going to look at how to handle exclusions. The assumption here is that you've worked with permutations, you've worked with combinations, you understand the difference between the two. All of that's from earlier lessons. So for today's, however, we're going to start with permutations of the letters in the word kitchen. And the reason for this video is to describe there's two different approaches for dealing with exclusions. The first is a direct approach. For starters here, I have 7 letters in the word kitchen, but the first letter cannot be a K in order to not begin with KI. So when I do that, I say there's 6 choices for the first letter, and then there's 6 letters left that could be arranged in any order to remain. Now, the problem, of course, is some people with this method, the direct method, is some people might actually consider this to be the final answer because if the word does not start with K, then it does not begin with KI, and so we're done. However, we have to also consider the fact that the first letter could begin with K, but then the second letter is not I. So that's another situation to have to consider. So another possibility is the first letter is K, so there's only one choice for that. The second letter is not I, so there's only 5 choices for that. And now there are, because K and I are both taken, and now there are 5 remaining letters left in the word kitchen that can be arranged in any order as you fit. And it turns out if you add 6 times 6 factorial plus 5 times 5 factorial, you get 4,920. Now, the whole purpose of this video is to discuss the exclusion principle, and you'll find that this is a slightly more elegant way to handle it, and it deals with a little bit less uncertainty, so to speak. So, to do this, all we have to do is remove any words that start with KI. So to do so, we simply say, all right, well, there's 7 factorial ways to permute the letters in the word kitchen. And that's all of the possibilities. And what I'll do is remove all of the situations where the first letter is K, which is only one chance out of 7 for the first letter to be K. The second letter to be I, there's only one way that that could happen. And then there's 5 factorial ways for the rest. And so basically, there's 5 factorial words that begin with KI. If we take those away from the 7 factorial permutations, we should have the same number. And it turns out to be true. You can see here that 7 factorial removing the 5 factorial gives us 4,920, but same does 6 times 6 factorial plus 5 times 5 factorial, same exact result. So this is direct and we consider all possibilities, and this is indirect. We just remove the possibilities we don't want from the total. This is far easier. So the second question is subtly different, though, because we do not have K or I in the first 2 letters. And so basically what we have to do here is say, this is the direct approach, as it were, that you have 5 choices for the first letter to not be a K or an I, and now you've used one of those letters already, so now there's 4 choices left for not K or I, and then we could also have the situation where there's IK. So there's KI or IK, and we've considered 2 of those options, and then we have 5 factorial for the remaining. That makes a total of 4,800. I'm realizing that that explanation is not very satisfactory. It's possible that my understanding is a little off, but rest for time at the moment, so I'm going to move on, but this is accurate. But again, it's still, even for me, who's not necessarily an expert on this, it could be some confusion. But using the elimination method, I have a lot more confidence because I'm able to see that we have the 7 factorial total 7-letter permutations, and then there's the words that start with K, and then I, and then have 5 other letters that could be in any order. And then there's also the word that begins with I and then K and has the 5 factorial permutations left over. And those are both being eliminated. So either way, no matter how I slice it, I use both approaches and I get the same result. First of all, 5 for the first letter, 4 for the second letter, 5 factorial for the remaining tiles, and then I consider that 2 different ways because the first 2 letters could it be K or I or K. And then the other one is just taking all the elimination. So now that you have that in mind, this could be a lot easier to use the elimination method, and it's a lot less painful. So you can see here it's a more challenging problem, but it's just talking about 26 letter tiles in a game. And if you're going to draw 7 from that pile of 26 at random, how many different ways could you get 7 letters so that 2 of them are vowels? I want to pay attention to the phrase "at least." So what they mean by at least 2 of them being vowels is we could have 3 vowels or 4 vowels or 5 vowels or 6 vowels or 7. 7 vowels isn't going to happen, but we could have all the way up to 5 vowels. This is only one of each letter. So the point is that to do this directly would be a painful process because we would have to count all the different possibilities for more than 2 vowels. Instead, what we're going to do is consider all the different ways that 7 tiles can be chosen from a set of 26. Notice that's 26 factorial less 19 factorial, so that's basically 7 different choices from a set of 26. But then, since you're drawing from a bag and you have tiles that the order does not matter, we're going to divide out all the different permutations of 7 letters or 7 tiles, and so we won't be counting those twice or multiple times. This shorthands into the combinatorics notation like vector notation or the 26C7, and that gives us the total arrangements or combinations of 7 tiles from a set of 26. But now what we have to do is exclude the situation where there are no vowels, and then you also exclude situations where there's just 1 vowel. So from the 5 vowels in the 26-letter alphabet, there's only one way to have no vowels, which means for the 26 remaining letters, there should be 7 consonants chosen. Similarly, to get 1 vowel, I take the 5 vowels and choose only 1, which there's basically 5 ways to do that. And then I'm going to take the remaining 21 letters, and I have 6 left to choose from. So this is all the ways that there could be all consonants, and this is all the ways there could be 1 vowel. We simply subtract from the original set of combinations both scenarios, and we get our combinations. Turns out to be accurate as well. I've checked it. So anyway, thanks for watching. Hope this is helpful. Have a good day.